Hello everybody, welcome into another lesson. So today we are going to talk about polar equations for conic sections. So yes, I know we've talked about conic sections to death in this unit, and you're all going to be happy. This is the final lesson of the unit, but it should come as no surprise to you that we can also have conic sections in the polar system. So in the polar system, your conic sections will take one of two forms. You have it where that's always how a polar equation starts out, r equal to something. In this case, it's equal to e times p over 1 plus or minus e cosine of theta. Well, what's e and what's p? E is that eccentricity. Yesterday we talked about eccentricity of a conic section. Well, that comes into play in this lesson. We are going to use the eccentricity to form a polar equation for a conic section. And then you have, if it's got x-axis symmetry, or if it's an ellipse, x would be the major axis, it's going to be divided by 1 plus or minus e cosine of theta. You could think of cosine of theta being r cosine of theta being x. So that's where that cosine comes in for x. And that p is the distance from the focus to the directrix. It's always going to be positive. So you take the distance from the focus to the directrix, you'll get p. Now, you have plus and minus. So when would you use plus, when would you use minus? Well, if the directrix is to the right of the focus, you would use plus. If that makes sense, you think of a number line, or even in the x-axis, you go to the right of 0, it gets positive. So you'd use plus e cosine of theta. If the directrix is to the left of the focus, you would use minus e cosine of theta. So left would be negative, if that makes sense. And then the other form is r equals EP divided by 1 plus or minus e sine of theta if it has y-axis symmetry, or the y-axis is the major axis for an ellipse. So when would you use plus, when would you use minus? Well, if the directrix is above the focus, you would use plus e sine of theta. If it's below the focus, you would use minus e sine of theta. You could think of y being r sine of theta, so that would help you identify which function you need to use. And then these help you identify which sign you need to use on the coefficient for your trig function in the denominator. Alright, so we've talked about all that. Now, something else worth mentioning, a couple things. The focus for today's lesson is going to be at the pole, at the point 0, 0, for every exercise we do. So that's going to make life a lot easier. These can always be applied to where the focus is not at the pole, but a focus at the pole at the point 0, 0 is going to make life so much easier. And then we also have to talk about the directrix. We know in a parabola, the vertex of the parabola is exactly halfway between the directrix and the focus. So we don't really need to use these formulas for that, though we technically could. But these formulas come into play when you have the when you're talking about ellipses and hyperbolas. Ellipses actually have two directrices. That would be the plural form, directrices. A hyperbola has one directrix, where some people would think the hyperbola's directrix would be literally the line right through the center of the hyperbola. It's actually not. It's a line that runs parallel to the center. But if the conic section has x-axis symmetry, or if it's an ellipse with the x-axis being the major axis, the equation of the directrix is either going to be plus or minus a over e times x. Well, e, of course, is your eccentricity. A is the length of your major axis going from the center to the vertex. And then times x, if that makes sense, because it's x-axis symmetry. And then same thing with the y. It would be a over e times y for your directrix, plus or minus, depending upon which direction it's going. But what is true for all these conic sections is that the vertex is always between the focus and the directrix. It's just for an ellipse and in a hyperbola, they're not exactly halfway between. The difference is it's a different amount of units between each. So it's not evenly between. That's where these equations come into play for finding the directrix of an ellipse or a hyperbola. But having said that, let's go ahead. For the first few exercises, we're just going to be given the polar equation of a conic section, and we're going to identify what it is. So let's go ahead and do that. This will actually probably be the easiest part of the lesson. Alright, so we've been given r equals 2 over 1 minus cosine of theta. R equals 2 over 1 minus cosine of theta. Alright, so all we're trying to do is identify what type of conic section this is. When you're trying to do that given a polar equation, ignore your numerator. We don't care what's in the numerator. You only want to look at your denominator. Now, a couple things. You want the constant term in the denominator to be a positive 1, which we have here. Part 1 checks out. Now, the second thing is that coefficient, regardless of whether it's positive or negative, the coefficient on your trig function is your eccentricity. Well, the coefficient on the cosine is 1, so we've established this conic section has an eccentricity of 1. Well, a conic section with eccentricity equal to 1 is a parabola. So we can easily identify this conic section as a parabola. That's exactly what you would have. This is a parabola. Let's do another one. So r equals 2 divided by 1 plus sine of theta. Alright, so we've been given r equals 2 over 1 plus sine of theta. Well, again, ignore the numerator. We don't care about that. Just look at your denominator. Your constant term's a positive 1, and then if you look at your coefficient on that sine, regardless of whether it's positive or negative, your coefficient is 1, meaning your eccentricity is 1. And if it has an eccentricity of 1, it's a parabola. And parabolas are probably the easiest conic section to identify because the eccentricity is always 1. Where it gets a little bit trickier is when you get into ellipses and hyperbolas, which we're going to go for next. Alright, so we have r equals 4 all over 4 minus the cosine of theta. So r equals 4 all over 4 minus the cosine of theta. Well, what holds true universally is forget what's in the numerator. We don't care about the numerator, just look at your denominator. If you look at your denominator, your constant term is a 4. It needs to be a positive 1. So what we have to do with the denominator is we need to factor out a 4, right? So this would turn into 4 all over 4 times 1. Now we made that constant term of 1 minus, well, 4 times what gives us a coefficient of 1? That'd be 1/4. 4 minus 1/4 cosine of theta. Once you've completely factored the denominator, you look at the parentheses. You don't even care about the 4 outside the parentheses. Just look at what you have in your parentheses. Your constant term is now a 1, and then your coefficient on the cosine term is 1/4. which means you have an eccentricity of 1/4. Well, we talked about yesterday, if you have an eccentricity greater than 0 but less than 1, it's an ellipse. So this particular conic section is actually an ellipse. That's what we would have with an eccentricity of 1/4. You end up having an ellipse. All right. Now, let's see. Let's do some more. I got 3 more of identifying, then we're going to set up some equations. All right, let's say we have r equals 7 all over 7 plus sine of theta. So r equals 7 all over 7 plus sine of theta. What kind of conic section is this? Again, forget your numerator. We don't even care about the numerator, but look at your denominator. That constant term needs to be a 1, and right now it's a 7, so we need to factor out a 7. So r is going to equal 7 all over, we factor out that 7 times 1. We just made the constant term a 1, plus this would be 1/7 sine of theta. And of course, if you distribute that 7 through, you get the original denominator. But what we really look for identifying the conic section is what's inside the parentheses. The constant term is now 1. The coefficient on your sine is 1/7, which means you have an eccentricity of 1/7. Well, 1/7 is greater than 0 but less than 1, so this makes this an ellipse. So this particular conic section also would happen to be an ellipse. All right, I got 2 more I'd like to do. All right, we have r equals 3 all over 4 minus 8 cosine of theta. So we have r equals 3 all over 4 minus 8 cosine of theta. Again, forget your numerator, just look at your denominator. That constant term needs to be a 1, so we got to factor out a 4 in the denominator. So r is going to equal 3 all over 4 times the quantity of 1. Factoring out a 4, this would be minus 2 cosine of theta. So now the denominator is completely factored. We have a constant term of 1. Now look at your coefficient on the cosine. It's 2. So that means you have an eccentricity of 2. Whenever the eccentricity is greater than 1, this is a hyperbola. So this particular conic section would actually be considered a hyperbola, because the eccentricity ends up being greater than 1. Let's do another one, and then we're going to change gears a little bit. Alright, r equals 10 all over 3 plus 9 sine of theta. So we have r equals 10 all over 3 plus 9 sine of theta. Again, forget your numerator, just look at your denominator. The constant term's a 3, we need to make that a 1. So we'll factor out a 3 in the denominator, so r is going to equal 10 all over 3 times, we factor out a 3, this would turn into 1 plus 3 sine of theta. Now what we look for is what's inside the parentheses. Your constant term's a positive 1, and then the coefficient on your sine of theta is a 3. That means your eccentricity is 3. And if you have an eccentricity greater than 1, this is a hyperbola. So this particular conic section is actually going to be a hyperbola. Alright, so as you see, identifying conic sections is relatively easy when it comes to using the polar equation. It's actually surprisingly easy. Now, for the next few exercises, we're going to be given some what type of conic section we're dealing with, the eccentricity in the equation of the directrix, and the focus will be at the pole. It's going to be up to us to find an equation for that conic section in polar form. So we're going to start with parabolas. So we're going to be given, for the next couple of exercises, this one we have a parabola. The eccentricity is always 1 for a parabola. And then the directrix is going to be at x equals -1. The focus is at the pole, which is going to be at 0, 0. Which also works out to 0, 0 in rectangular form. Okay, so we have a parabola where the eccentricity is always 1 for a parabola. Directrix equals -1. The focus is at 0, 0. Well, a couple of things we need to look for. We need to look for the eccentricity, which we already have. The next thing we need to find is P. P is always the distance from the focus to the directrix. Well, you have an x-coordinate of 0, x-coordinate of -1. Well, it's just a distance of 1. So, therefore, you have P equals 1. Now, let's go ahead and set up our equation here. Let's just start with the general form. R equals EP all over 1. Now, the x-axis is the major axis because the directrix always gives which axis is the major axis, or what axis it has symmetry with. If it's x-axis symmetry, it's going to be a form of E cosine of theta. Now, is it going to be plus or minus? Well, notice the directrix is to the left of the focus, to the left of the pole, so actually it's going to be minus. So now we've got a general form set up. Let's just plug in all these values. R equals E, which is 1, times P, which is 1. 1 times 1 is 1. All over 1 minus your eccentricity of 1 times the cosine of theta. So in polar form, you get the equation of this conic section being R equals 1 all over 1 minus cosine of theta, based on what we plugged into the formula. Now let's do another parabola. I'll even leave that up. So alright. Actually, no, I'm not, because it could change. Okay, so we've been given a parabola where the eccentricity is always 1. The directrix is at y equals -4. The focus is still at 0, 0, the pole. So what I'm going to recommend is next we find P. Well, what is P? That, again, is the distance from the focus to the directrix. So a y-coordinate of 0 to a y-coordinate of -4, that's going to give you a distance of 4. So P is going to equal 4 in this case. Now that we know E and P, let's go ahead and start setting up our equation. Let's work with the general formula for it first. So R always equals EP all over 1. Now let's figure out which function we're going to use. Since the directrix is y equals, that means this parabola has y-axis symmetry. So it's going to be of the form E sine of theta. Now, is it plus or minus? Well, notice the directrix is below the focus, below the pole, so it'll be minus E sine of theta. Now all we have to do is take everything and plug it in. So E is 1 times P is 4. Well, 1 times 4 is 4. So this will be 4 all over 1 minus your eccentricity of 1 times the sine of theta. So in the end, you get the polar equation r equals 4 all over 1 minus sine of theta in polar form. So as you see, parabolas are pretty dang simple. Now it's going to be a bit different when we get into ellipses and hyperbolas, but the next two we're going to do ellipses where everything's given to you. The focus is still at 0, 0, but your E and P are going to change. So let's go ahead and do that here. Alright, so we are dealing now with an ellipse where the eccentricity is 1/2. The directrix is at y equals 1. So we have an ellipse with eccentricity of 1/2. The directrix is at y equals 1. The focus is at 0, 0 at the pole. Well, we already know the eccentricity. Next thing we need to do is find P. That's the distance between the focus and the directrix. Well, a y-coordinate of 0 to a y-coordinate of 1, that's a distance of 1. Now we can set up the general formula for a conic section in polar form. R is going to equal, of course, EP all over 1. Now, which function are we going to use? Since the directrix is y equals, that tells you this ellipse has the y-axis being the major axis. So it'll be in the form of E sine of theta. And then notice your directrix is actually above the focus, so it's going to be plus E sine of theta in this case. Knowing everything we know now, let's plug this into the formula. So R equals, so E is 1/2, P is 1, half times 1 is 1/2, all over 1 plus your eccentricity of 1/2 times E sine of theta. But in general, what we really want to do for the final answer is get rid of the fractions and clean this up a bit. Isn't it true that 1/2 in the numerator? So let's say I have 1/2 over 1. Isn't that the same as just 1 in the numerator with that 2 moved to the denominator? That's exactly what we're going to do here. So what I can do is I can change my numerator to just be 1. That 2 will go down to the denominator times that 1 plus 1/2 E sine of theta. Or actually, the E is gone because your E is 1/2. I don't know why I keep putting E. So then R would equal, when you distribute the 2, would equal 1 all over 2 plus sine of theta. So the polar equation for this particular ellipse is R equals 1 all over 2 plus sine of theta. Now let's do another ellipse, a very similar style to this. Alright. We have an ellipse with eccentricity of 3/4. The directrix will be x equals -4. Alright, so we have an ellipse with eccentricity of 3/4. Directrix is x equals -4. Focus is still at 0, 0. Well, we know E, let's find P next. That again is just your distance from the focus to the directrix, so an x-coordinate of 0 to an x-coordinate of -4, that's a distance of 4. So P equals 4. Now, let's just do E times P real quick. E times P, that just equals 3/4 times 4, which would just give you 3, right? So E times P is 3. Okay. Well, let's now get the general formula going for this ellipse. So it always starts out as E times P all over 1. Now, notice this time the directrix is x equals. That means the x-axis is the major axis for this ellipse, so it's going to be e cosine of theta. Now, is it plus or minus? Well, the directrix is to the left of the focus from the pole, so it'll be minus e cosine of theta. Giving everything we have now, let's plug it into the formula. So r is going to equal that e times p, which we've already determined was 3, all over 1 minus our eccentricity of 3/4 cosine of theta. Okay, we're almost done, but we want to get rid of the fraction. We need to clean this up for the final answer. Well, if you multiplied the denominator by 4, you would definitely get rid of your fraction, wouldn't you? However, we can't change the original equation. If we multiply the denominator by 4, we also have to multiply the numerator by 4. So we'll multiply that denominator by 4. So 4 times 1 minus 3/4 cosine of theta. And then in the numerator, this would turn into 4 times 3, because if you cancel out the 4's, you're back with the original, and you're not actually changing the original equation this way. Now, if we just multiply and distribute, you'll get your final answer. R would end up equaling 12 in the numerator, divided by 4 minus 3 cosine of theta. So the final answer for this particular equation of the ellipse is r equals 12 all over 4 minus 3 cosine of theta. Alright, so you know what's coming now, hyperbolas. We knew it was coming. Good news is the focus will still be at 0, 0, but we know for the next two we're dealing with hyperbolas. The eccentricity in this case is 2. The directrix will be at x equals 1. So we have a hyperbola with eccentricity of 2. Directrix at x equals 1, the focus at 0, 0. We know the eccentricity, let's find p, which is the distance from the directrix to the focus. Well, an x-coordinate of 0 to an x-coordinate of 1, that's a distance of 1, so p equals 1. Okay, now let's plug in let's start with a general formula for a conic section. R equals EP all over 1. Now, notice here how the directrix equation is x equals. That means then that the x-axis is the axis of symmetry. So we're going to use e cosine of theta. Now, is it plus or minus? Well, the directrix is to the right of the focus, the right of the pole. So actually then this will end up being plus. So you'll have EP over 1 plus e cosine of theta. Now we have sufficient information to go ahead and form the equation. So R equals, alright, E is 2, P is 1, 2 times 1 is 2. So this will be 2 all over 1 plus the eccentricity is 2, and then cosine of theta. So the equation that we should get in polar form is R equals 2 all over 1 plus 2 cosine of theta. One more of these, then we got one final frontier to cross where we're going to be given even less information and have to figure out a little bit more. Alright, a hyperbola with eccentricity of 3/2. The directrix will be at y equals -1. Alright, so we have a hyperbola with eccentricity of 3/2, and then the directrix is at y equals -1, focus is at 0, 0 at the pole. So Let's find P. P is always the distance between the directrix and the focus. A y-coordinate of 0 to a y-coordinate of -1, that gives you a distance of 1. Now let's go ahead here. Let's build the general formula for a conic section. R equals EP all over 1, and then which trig function are we going to use? Well, the directrix is y equals, which tells you this hyperbola has y-axis symmetry. So it'll be a form of e sine of theta. And then is it plus or minus? Well, notice your directrix is below the focus, so it'll end up being minus e sine of theta. Now we have sufficient information to go ahead and find the equation. So R equals E times P. Well, E is 3/2, P is 1, 3/2 times 1 is 3/2, all over 1 minus that eccentricity of 3/2 times the sine of theta. Well, we definitely need to clean this up and get rid of the fractions. That 3/2 would be the same thing as kicking that 2 out of the numerator, putting it in the denominator. So this would be the same thing as 3 all over 2 times 1 minus 3/2 sine of theta, which for the final answer, we'll just distribute that 2 in the denominator. This ends up R equals 3 all over 2 minus 3 sine of theta. So this equation in polar form should end up being R equals 3 all over 2 minus 3 sine of theta. Okay, so these really weren't that bad. They pretty much handed us everything. Now for the next few, they're not going to. You're just going to be given what type of conic section you have and what the vertex is. And you have the focus at the pole. That's all you're given. So we'll go back and start with some parabolas. Those are probably the easiest to start with. We had to figure out the directrix and all that. So we are given a parabola. We know the focus is at the pole at 0, 0. Well, let's see. The vertex, they tell us, for this parabola is at 1 negative pi over 2. So it's actually polar coordinates for the vertex. Well, do yourself a favor. Eccentricity is one of the things we need to find. A parabola always has an eccentricity of 1. So that's a freebie. Eccentricity on a parabola is always 1. Now, what we need to do is go ahead here, find the rectangular coordinates for this vertex. It's going to come in handy. You're going to see why. Well, we're going to convert that 1 negative pi over 2 into rectangular. Well, okay. So x always equals r cosine of theta. So in this case, that would be 1 times the cosine of negative pi over 2. Well, cosine of negative pi over 2 is 0. 1 times 0 is just 0. And then y equals r sine of theta. So 1 times the sine of negative pi over 2. The sine of negative pi over 2 is -1. Then times 1, that's -1. So in rectangular coordinates, you get the vertex to be 0, -1. So now we've got this in a form we can work with. The focus is at 0, 0. The vertex is at 0, -1. Now, a parabola is nice because the vertex is exactly halfway between the focus and the directrix. It's between. So if the focus is at 0, 0, the center is at 0, -1, that means then the difference between the distance between the vertex and the focus is just a length of 1, which means that the distance between the vertex in the directrix also has a length of 1, but it would end up being below the vertex. You would end up getting a directrix then at y equals -2. So you'll have a directrix now at y equals -2. So we got the equation of the directrix, we got the eccentricity. What's left now is to find p, the distance between the focus and the directrix. Well, p then is going to be, so we go from a y-coordinate of 0 to a y-coordinate of -2, that means p has to equal 2. Now let's start working with a general formula for the equation of a conic section. That always equals EP all over 1, and then which function are we using? Well, the directrix is y equals, that tells you this parabola has y-axis symmetry, so it's going to be of the form e sine of theta. Now, is it plus or minus? Well, the directrix is below the focus, below the pole, so it's going to be minus e sine of theta. Knowing what we know now with all this information, we can proceed to find the equation. So r equals e, which is 1, times p, which is 2. 1 times 2 is 2. All over 1 minus your eccentricity is 1, so this would just be 1 minus sine of theta. So the polar equation of this parabola in this case should be r equals 2 over 1 minus sine of theta. I got one more, parabola, then we'll move on to ellipses. Well, I could actually, if I'm doing a parabola, I can keep that eccentricity of 1 up there, but we will have the vertex at 5 pi. So the vertex of this parabola is at the coordinate 5 pi in polar coordinates. The focus is still at 0, 0. Well, eccentricity is always 1 for a parabola, so we got that going for us. But first thing I would suggest, convert this polar coordinate into a rectangular coordinate. So x always, here, let's do this. So that 5 pi, we're going to convert that into rectangular. X always equals r cosine of theta, so this would be 5 times the cosine of pi. Cosine of pi is -1 times 5 equals -5. And then your y is always r sine of theta, so it would end up being 5 sine of pi. Well, the sine of pi is 0, then times 5, well, that's 0. So this turns the rectangular coordinate into -5, 0. So now we found the rectangular coordinate to be -5, 0. Okay. Now, what is true here? Again, for a parabola, the vertex is exactly halfway between the focus and the directrix. So, your vertex then, halfway between the focus and directrix, you have a difference of 5 in the positive direction for going to the focus. That means your directrix has to go back 5 units. So that means the directrix would have to be at x equals -10. Alright, so now we got the directrix, we can now find p. And again, p is the distance from the focus to the directrix. An x-coordinate of 0 to an x-coordinate of -10, that's a distance of 10. So now we got p to be 10. Let's go ahead and set up the general formula for the equation of a conic section. R equals EP all over 1, and then which function are we using? The directrix is x equals, so that means this parabola has x-axis symmetry. So it'll end up being of the form e cosine of theta. And the directrix is to the left of the pole, the focus, so it'll be minus e cosine of theta. Now we have sufficient information to find the equation. So r would equal e times p. Well, e is 1, p is 10, 1 times 10 is 10. So this will be 10 all over 1 minus your e, which is 1, cosine of theta. So in this case, the polar equation we should be looking for is r equals 10 all over 1 minus cosine of theta. All right, those were easy. Next, we're going to do some ellipses. It gets a little bit harder when we get into ellipses and hyperbolas. We're going to have to find the directrix, the eccentricity, all that. They'll give you, we have the focus being 0, 0, a focus for an ellipse. That's all we need is one of them. But we got to find everything else. The vertices in this case are at 2, 0, and then also 10 pi. Of course, that makes sense. The vertices, you would have two vertices on an ellipse, and these would always refer to the major axis. So let's go ahead, let's convert these polar coordinates into rectangular coordinates. So 2, 0, well, okay, so x equals r cosine of theta, so 2 cosine of 0. Well, cosine of 0 is 1 times 2 is 2. Then y equals r sine of theta, so 2 sine of 0. Well, the sine of 0 is 0 times 2 is 0. So what do you know? In the rectangular system, 2, 0 stays 2, 0. That hasn't changed. Now, what is going to change is this 10 pi. Let's work on 10 pi. What would that look like in the rectangular system? So x, again, r cosine of theta, so 10 times the cosine of pi. Well, cosine of pi is negative 1 times 10. That would end up giving you negative 10. Y equals r sine of theta, so 10 times the sine of pi. Sine of pi is 0 times 10 is 0. So 10 pi in the rectangular system would be the ordered pair negative 10, 0. So now we have vertices for this ellipse at 2, 0, negative 10, 0 in the rectangular system. These are very important because next thing you want to do, if all you're given is the vertices and the focus, you probably want to go ahead and find the center. So let's go ahead and find the center. The center is always halfway, of course, between your vertices. So let's use the midpoint formula. So x1 would be 2, x2 would be negative 10, so 2 minus 10 all over 2, and then you would have 0 plus 0 all over 2. Well, 2 minus 10, that turns into negative 8 over 2, and then you'll have 0 over 2. Which then finally means that your center should be at negative 4, 0. So now you have the center of this ellipse located at negative 4, 0. Let me move this up some. So we've identified the center to be at negative 4, 0. All right. Where do we go from there? We don't even know our eccentricity yet. We do know a focus, which helps us. Well, if we go from the center to the focus, that's going to give us our length of c, right? Because the focus always goes based on the length from the center. So from an x-coordinate of negative 4 to 0, that's a distance of 4. That means that our c value, the length of the focus, has to be 4. Okay, we need to find a, however. Well, let's just go from the center to one of these vertices, just one of them. If we go from an x-coordinate of negative 4 to negative 10, that's a distance of 6 units, right? So that means a has to be 6. Well, good news is now, we have enough information to find the eccentricity at least, because the eccentricity is always c divided by a. Well, c is 4, a is 6, which means we simplified as 2/3. You have an eccentricity of 2/3, which matches with that of an ellipse. Now, let's next thing we got to do is worry about finding the directrix. That's something we don't have yet, which polar equations rely on. Okay, so now it's true that for an ellipse or a hyperbola even, your vertex is still, it's just between the directrix and the focus, but it's not halfway between like it is for a parabola. So let me just draw some ellipse here. You're going to have two directrices somewhere outside of the ellipse. So you can expect the directrices to be somewhere outside of the ellipse. And for this particular conic section, we just need one of the directrices to form an equation. So if we remember what the equation is for finding the directrix of an ellipse, well, it's always going to end up being the directrix equals a, it's going to be plus or minus a over e, and then times the variable that's your major axis. Well, it looks like the x-axis is the major axis, right? From 2, 0 to negative 10, 0. So this will be a over e times x. Well, notice your focus is 0, 0. You have a vertex at 2, 0. That means your directrix would have to be outside of the ellipse, to the right of it somewhere. So we're just going to use the plus form in this case. Well, what is a? A is 6, and then e we determined was 2/3. So 6 over 2/3 times x. Well, we have a complex fraction. So what is 6 over 2/3? That's the same thing as 6 over 1 times 3 over 2. 2 goes into 6 3 times, so this would just end up being 9. So you have a directrix for x equals 9. So directrix is actually all the way at x equals 9. So that just shows you how unequal everything is. Okay. I should say that x equals that, excuse me. Alright. Now, we got the directrix. We need to find p because we have the focus. If you go from an x-coordinate of 0 to an x-coordinate of 9, you get a distance of 9, so p equals 9. Alright. Let's start building now the general formula for a conic section. R equals EP all over 1. Now, which function are we using? We notice that the directrix is of the form x equals, so this means we have an x-axis being the major axis, so we'll use e cosine of theta. And notice how the directrix is to the right of the pole, the focus, so it'll be plus e cosine of theta. Now let's take everything we found and let's plug that into this formula. So R equals E, which is our eccentricity ended up being 2/3, times our P of 9, all over 1 plus our eccentricity of 2/3 times the cosine of theta. First, let's simplify the numerator. 9 times 2/3, that's just going to turn into 6, all over 1 plus 2/3 cosine of theta. Well, we need to get rid of the fraction from the denominator, don't we? So, let's multiply by 3 to get rid of the fraction, but we can't change the overall value, so we got to also do that to the numerator. So we'll take 3 times 6 all over 3 times 1 plus 2/3 cosine of theta, which now we have a final answer when we simplify this. 3 times 6 is 18. All over 3 times 1 is 3, plus 3 times 2/3 is 2, and then the cosine of theta. So the polar form of this equation should end up being r equals 18 over 3 plus 2 cosine of theta, once we found all our information. Alright, let's go through another ellipse, and then we'll move into a couple of hyperbolas. Alright. Good news is the focus is still at 0, 0. We can still work with that, but we are given vertices this time in different places. One vertex is at 2 pi over 2. Another vertex will be at 4, 3 pi over 2. So our vertices, all we're given is that this is an ellipse with vertices at 2 pi over 2, 4, 3 pi over 2, and a focus at 0, 0. We don't know anything else yet. First things first, I would suggest converting these polar coordinates into rectangular coordinates. So let's convert that 2 pi over 2 into a rectangular coordinate. Okay, so x equals r cosine of theta, so that would equal 2 times the cosine of pi over 2. Well, the cosine of pi over 2 is 0, then times 2 is 0. Y equals r sine of theta, so 2 times the sine of pi over 2. Well, the sine of pi over 2 is 1 times 2 is 2. So 2 pi over 2 turns into a rectangular coordinate of 0, 2. Alright, so we got 0, 2 as the rectangular coordinate there. Now let's find one for 4, 3 pi over 2. So let's convert that to rectangular. 4, 3 pi over 2 into rectangular form. X equals then 4 times the cosine of 3 pi over 2. Well, the cosine of 3 pi over 2 is 0 times 4 is 0. And then y would equal 4 sine of 3 pi over 2. Well, the sine of 3 pi over 2 is negative 1 times 4 gives you negative 4. So 4 3 pi over 2 becomes 0, negative 4 in the rectangular system. Alright, so we've got our two vertices converted to rectangular coordinates. We're off to a good start there. Well, next thing you want to do is find your center. Always start out by finding your center next. So we're going to use the midpoint formula between these two coordinates. Well, x1 is 0, x2 is 0, so 0 plus 0 over 2. x1 is 2 plus y2 is negative 4, so 2 minus 4 over 2, which would simplify into 0 over 2, and then negative 2 over 2. So your center of this particular ellipse is going to be at 0, negative 1. So now we found the center is going to be at 0, negative 1. Alright, so we can now find A and C, because A always goes from the center to a vertex. Well, we can tell this is definitely going to be the y-axis is the major axis. Why don't we write that? Y-axis major, because that'll help us set up the equation and find the Directrix equation as well. So if you go from a y-coordinate of -1 to a y-coordinate of -4, that's a difference of 3, isn't it? So that means A has to equal 3. And then from the center to the focus is your C. If you go from a y-coordinate of -1 to 0, that's a distance of 1. So C equals 1. Now, we have C, we have A, we can find our eccentricity. Eccentricity, again, is always C over A. Well, C is 1, A is 3. So you have an eccentricity of 1/3 for this particular ellipse. Alright, now, we need to find the directrix. We know the y-axis is the major axis, so it's going to be in the form y equals, we have an A over E, but here's the thing, is it plus or minus? Again, your vertex is always, it's not necessarily halfway, it's not going to be halfway, but it's definitely between the directrix and the focus. If you have a vertex at, pick any vertex, you have 0, 2, you have a focus at 0, 0, that means then your directrix has to be outside, which would end up being plus. We can use plus. We could have gone to the left and got a minus also, but it's really going to shake out the same. I prefer to work with positive if at all possible. So A over E, well, let's see. So y equals positive A over E. That's 3 over 1, or just 3. So we have a directrix through y equals 3. Alright, so we found the directrix. Now the next thing to do is find the value of P, which is the distance between the focus and the directrix. If you go from a y-coordinate of 0 to a y-coordinate of 3, that's a distance of 3. So we get P equals 3. Now we're just about there. We can start setting up the equation. Let's work with a general form first. R equals EP all over 1, and then which function are we using? Notice the directrix is y equals, so that's going to put us in the form of E sine of theta. Now the directrix is above the pole, above the focus, so this will end up being plus. We have enough information now to go ahead and find the equation and plug it into the formula. So E is 1/3 times P is 3. 1/3 times 3 is actually 1. All over 1 plus your eccentricity of 1/3 times the sine of theta. Well, we definitely want to clean up this fraction, so we're going to multiply both numerator and denominator by 3 because we actually have to keep this equal. So you'll have 3 times 1 over 3 times 1 plus 1/3 sine of theta. So for your final answer, R should equal 3 all over 3 plus sine of theta. So you'll end up getting that R equals 3 all over 3 plus sine of theta for the polar form of this equation. Alright, now we got a couple hyperbolas, then we'll be done with the lesson. The focus will still remain at 0, 0. A focus will. We'll work off that focus. But for the next two exercises, or I should say the last two, we're going to be dealing with hyperbolas. So we have a hyperbola here with a vertex at 1 3 pi over 2. and another one at 9 3 pi over 2. So all we got for this particular hyperbola are the vertices and a focus at 0, 0. We're going to have to do a little bit of work to find the eccentricity and all that. So first thing, again, find the convert these polar coordinates to rectangular coordinates. So let's start with that 1 3 pi over 2. Let's convert that to rectangular. So x would equal 1 times the cosine of 3 pi over 2. Well, the cosine of 3 pi over 2, as we know, is 0. 0 times 1 is 0. And then y equals 1 times the sine of 3 pi over 2. Well, the sine of 3 pi over 2 is -1 times 1 gives you -1. So you would end up getting a rectangular coordinate of this being 0, -1. And since you have the same angle, just a different radius, your 9 3 pi over 2 would actually just turn into 0, -9. So that would give you a rectangular coordinate of 0, -9 for that one. Alright, so that saved us a little bit of work. So next thing to do here, find the center of the hyperbola. Let's go ahead and do that. So again, let's use the midpoint formula. So the center, so we have an x1 of 0 plus an x2 of 0 all over 2. Then we have an y1 of -1 plus a y2 of -9, so -1 minus 9 over 2, which is going to turn this into 0 over 2, -10 over 2, which means your center of this hyperbola is going to be at 0, -5. Alright, so we just found the center of this hyperbola to be at 0, -5. Well, we need a couple pieces of information here. Why don't we find A? A is always the distance from the center to a vertex. Well, if we go from a y-coordinate of -5 to a y-coordinate of -9, that's a distance of 4, right? So that means A has to equal 4. And then we want to find C, which is the distance from the center to a focus. If we go from a y-coordinate of -5 to a y-coordinate of 0, that's a distance of 5. So C is going to equal 5. We have A, we have C, we actually have enough to find the eccentricity now. So E always equals C over A. Well, C is 5, A is 4, we have an eccentricity of 5/4, which would coincide with the fact of it being a hyperbola with an eccentricity greater than 1. So we know we're on the right track. Now, next thing we need to do is work on finding the directrix. Now, it's true that, again, a vertex is always in between a directrix and a focus. So, if we have a focus at 0, 0, and we'll even work with 0, -1, right? We have a vertex at 0, -1. We have a focus at 0, 0. Why don't we then work on finding that directrix? So we know then that the directrix is going to have to occur somewhere in between. It's going to have to actually then, your vertex, it would have to occur above it then. Or actually below it. It'd have to occur below it because vertex is in between the focus and the directrix. So it'll be below this point. So for a hyperbola also, now what axis is the major axis? Or what's the axis of symmetry? You got y-axis symmetry, which means then that your directrix will be in the form y equals A over E, well, 4 over 5/4, but we know the directrix is going to be below the pole. It's going to be below this vertex of 0, -1, so it's actually going to be a minus on there. And we get a complex fraction of -4 over 5/4. Let's convert this. Let's invert and multiply. So you'll have -4 over 1 times 4 over 5, which would make your directrix end up being y equals -16/5. So your directrix in this case is y equals -16/5. Now that we found the directrix, we can find p, because that's just the distance from the focus to the directrix. The focus is 0, 0. If you go from a y coordinate of 0 to a y coordinate of -16/5, well, that's a distance of 16/5. So we found p to end up being 16/5. Now we have enough information to start finding the equation. First, let's get the general formula. R equals EP all over 1, and then which function are we using? Well, it's got y-axis symmetry, so we're going to use the form of E sine of theta. And notice your directrix is below the pole, below the focus, so this will be minus E sine of theta. We now have sufficient information to plug in everything to the formula and find the equation. So R equals that E of 5/4 times the P of 16/5 all over 1 minus your eccentricity of 5/4 sine of theta. Let's simplify this here. So your 5's will cancel out. 4 goes into 16 4 times. This would turn into 4 all over 1 minus 5/4 sine of theta. But of course we want to get rid of that fraction in the denominator, so we need to multiply both numerator and denominator by 4. So let's just write this here. You'll end up having 4 times 4 all over 4 times 1 minus 5/4 sine of theta, which now we should be able to get our final answer. In the numerator, that would turn into 16 all over 4 minus 5 sine of theta. So the polar equation of this particular hyperbola should be 16 over 4 minus 5 sine of theta. And I got just one more and we're done with the lesson. Focus stays 0, 0, which is nice. You know, some books will call it ED instead of EP. Just keep that in mind, but it means the same thing as far as your distance from the focus to the directrix. Alright, whoops, we're definitely going to have different vertices here. We're not keeping the same vertices, not at all. We have a vertex at 4 pi, and then we have one at 1, 0. So we have two vertices for this hyperbola, one at 4 pi, one at 1, 0. And we know the focus is, one of the foci is 0, 0. Let's go ahead and start converting these into rectangular coordinates. Well, good news is 1, 0 stays the same. 1, 0 will stay the exact same in rectangular, but when it comes to the 4 pi, so x would equal 4 times the cosine of pi. Well, the cosine of pi is -1. -1 times 4 is -4. Y equals 4 times the sine of pi. Well, the sine of pi is 0 times 4 is 0. So you actually end up with this rectangular coordinate being -4, 0. So you have a hyperbola here with both of your vertices having x coordinates, the y coordinate 0. So I think it's safe to say this has x-axis symmetry, which is going to help us here in the end to form the equation of the directrix and to form the final equation. Okay, now we've found the vertices in rectangular form. Let's find the center. So the center, well, that's going to be then, take your x1 of 1 plus your x2 of negative 4, so 1 minus 4 over 2. y1 and y2 are both 0, so 0 plus 0 over 2. Well, that means your center is none other than negative 3/2, 0. So the center of this particular hyperbola is at negative 3/2, 0. Now that we've been given the center, we can find C and A. If we go, let's say we want to find the distance between 1 and negative 3/2 for our x coordinates. That's going to be our A, from the center to a vertex. So 1 minus negative 3/2, well, that'd be 1 plus 3/2. You would actually have a distance of 5/2. So that means A has to equal 5/2. Alright, now to find your length of C, you're going to go from the center to the focus. Well, negative 3/2 is 0. That gives you a C of 3/2. Alright, so there's your hyperbola. With those A and C. Well, now we can find the eccentricity. That, of course, is C over A, which would give you 3/2 over 5/2, which is 3 over 2 times 2 over 5. Well, that didn't work out. Because you're going to get the eccentricity being less than 1. I kind of made up this example, so let's do a better example if you don't mind. This is why I stick to the book, because well, let's do something similar. We have 4 pi, 1 pi. That won't be too bad. I think we kind of have a good grasp on how to convert these coordinates into polar form. From polar to rectangular, 4 pi would end up being negative 4, 0. And then your 1 pi would just end up being negative 1, 0. Alright, I think we have a good grasp on those vertices. Now, the center. Alright, so we got the center then. That'll be our x2 of negative 4 plus our x1 of negative 1. So negative 4 minus 1 over 2, and then 0 plus 0 over 2. There we go. That means your center would have to be at negative 5/2, 0. Alright, so we have a center at negative 5/2, 0. We can find A and C. If you want to go from negative 5/2 to negative 1, that A would be a distance of 3/2. And then your focus is at 0, 0. If you go from negative 5/2 to 0, 0, that's a distance of 5/2 for your C. There we go. I can make this work. Now we have A and C. Let's find the eccentricity. So E equals C over A, which in this case is 5/2 over 3/2, which will invert and multiply the fraction. That would be 5 over 2 times 2 over 3. Well, that gives you your eccentricity then to be 5/3, which falls in line for a hyperbola being greater than 1 with the eccentricity. So that actually works. Okay. We got the eccentricity. Next thing we need to do is find the directrix. Well, if we have, notice we have changes in the x-coordinates. So we have the x-axis as the major axis. Now, what about then the equation of the directrix? It's definitely going to be x equals, but it's true that a vertex is between the focus and the directrix. Well, it's definitely going to be negative, right? The directrix would definitely fall between both of your vertices, so this is going to be negative of a over e, which would be negative 3/2 over 5/3. So another fraction, we got to invert and multiply. This would be negative 3/2 times 3 over 5. Well, your directrix is going to be at negative 9/10. So you have a directrix at x equals negative 9/10. So that was a bit of a fun one to find. Now that we have the directrix, we can find p, which is the distance between the focus and the directrix. If we go from an x-coordinate of 0 to an x-coordinate of negative 9/10, well, p is going to equal 9/10. That's the distance. All right, so we have E, we have P. Let's go ahead and start using the general formula for the equation of a conic section. So R equals EP over 1. Now, which function are we using? If the x-axis is the major axis, this will be in the form of E cosine of theta. All right, now, is it going to be plus or minus? Notice your directrix is to the left of the focus, to the left of the pole, so that would be minus E cosine of theta. Now we have sufficient information to plug all this information into this equation and find the equation. So R equals that E, which is 5/3, times the P, which is 9/10, all over 1 minus your eccentricity of 5/3 times the cosine of theta. Well, let's simplify this a bit. 3 goes into 9 3 times. 5 goes into 10 2 times. So this would end up becoming 3/2. Nah, I don't want to make it that big. This would become 3/2 all over 1 minus 5/3 cosine of theta. Well, let's start by getting the numerator, getting that 2 out of the numerator. That's going to be the same as 3 over 2 times 1 minus 5/3 cosine of theta. Yes, we have a bit of a mess. This is going to simplify into 3 all over 2 minus 10/3 cosine of theta. Now, last but not least, we need to clean up this fraction in the denominator, so we need to multiply both numerator and denominator by 3 to get rid of that fraction. So this will be 3 times 3 all over 3 times the quantity of 2 minus 10/3 cosine of theta, which when we do the final multiplication and distribution, we'll get the final answer for the equation of this conic. So 3 times 3 is 9. All over the bottom, when you distribute, that would be 6 minus 10 cosine of theta. So the polar form of this equation would be R equals 9 all over 6 minus 10 cosine of theta. Alright, so that's it for this unit. Next lesson we start the brand new unit, which will actually be analytical 3D geometry. The next lesson will actually be fairly easy. We're just going to introduce a 3D coordinate plane, do the 3D distance formula, 3D midpoint formula, things like that. So I hope everybody has a great day. Take care.